Hello, and welcome to my tutorial about confidential computing with SUSE and AMD SEV-ES. My name is Jörg Rödel, and I'm a Linux kernel engineer in the SUSE Labs department. There I work on the Linux kernel on different areas, I/O memory management units and x86 architecture, but also on KVM virtualization and a little bit on PCI. For quite some time already, I also work on confidential computing topics. So I helped AMD to bring the Linux guest support for SEV-ES into the upstream Linux kernel with kernel 5.10. And I'm also organizing the confidential computing conference at Linux Plumbers, where the future developments of confidential computing in the Linux ecosystem are being discussed. What I'm going to talk about today. When I talk about confidential computing, I will mostly cover confidential virtual machines. So first of all, I will show how easy it actually is to attack a virtual machine, a standard virtual machine, and steal data out of that machine, data and secrets. Then I give an introduction to AMD SEV and SEV-ES and show how it works and can be used to mitigate this attack so the data can no longer be stolen from your virtual machine. Then I will focus on SUSE Linux Enterprise and show how you can run a confidential virtual machine with AMD SEV-ES and libvirt. Then Vasily will show you how to run a KubeVirt, how to run a confidential VM in Kubernetes with KubeVirt. And in the end, I will cover how to run an SEV VM based on SUSE Linux Enterprise in the cloud. But before we begin, I want to highlight our partnership with AMD on this topic. SUSE and AMD are partnering on confidential computing for quite some time already. Together we worked on several upstream projects to enable confidential computing capabilities and enable them for AMD SEV and SEV-ES. The projects include the Linux kernel, libvirt, KubeVirt, and even OpenStack. This enables SUSE also to bring these technologies into its product and make it available for our customers. And we continue our work with AMD, and we are still working on the next generations of confidential computing support in Linux. So now let's get started. Imagine a standard virtual machine, and how it can be attacked. So how does a virtual machine look like on the physical machine? So usually we have a physical machine, real hardware, which runs in hypervisor, an operating system in the hypervisor, and where several virtual machines can be running. The problem is that everybody with access to the physical machine, with root access to the physical machine, can access the memory of the virtual machines. It can basically access all memory of the physical machine, which includes the memory of the virtual machines. And with access to the virtual machine memory, everyone on the physical machine can steal data from it. So if any secret data is in the virtual machine's memory, then this can be stolen from the host, from the physical machine, and the virtual machine owner would not even notice that. This is usually not a problem when you trust your physical machine and the operators, but if not, then your data is not secure. So let's see how a virtual machine looks like. So this is I prepared a standard virtual machine with libvirt, pretty much standard SCSI disk on a VirtIO SCSI controller, VirtIO network card, 4 vCPUs, 1 GB of memory. So I use this command to install a VM, and the VM is running here. So yeah, this VM is a standard VM, nothing is encrypted. So let's see, we have some secrets in that VM. a secret password. So secret password in that VM and other secret data. And now I show you how easily this can be stolen from the host side with someone with root access. So this is a root shell on the host of that virtual machine. You can see it running here. So how we can steal data? First of all, we need to find out which process is running this virtual machine. This is usually a QEMU process. So we search the process list for QEMU, and we find that this is a QEMU process that runs our virtual machine, and it has this PID. So now we can use the command or the little tool I wrote for this, readmem. It can read memory and scan memory for patterns. It's a pretty small tool, only 271 lines of C++ code, so not much and quickly developed. So let's see, we search for a secret password in the VM, which is run by this PID, and see it finds several incarnations of our secret password in guest memory. So an attacker could easily steal the password we wrote to this file, no problem. The attacker can even search for other secrets. Let's see what we find when we search for OpenSSH. Oh, it gives us several private keys which are stored inside the VM, so this can be stolen too. Basically everything that is in guest memory can be stolen this way. And it's not very hard to do that with someone that has root access to the physical machine. And again, the guest owner or the guest has no way of noticing that. So we better shut down our virtual machine that our data can no longer be stolen. So this was a pretty easy attack, and it shows how vulnerable standard virtual machines can be when the host cannot be trusted, or the hypervisor or the host owner cannot be trusted. So how can you mitigate these attacks? There's a technology in AMD processors called SEV, or Secure Encrypted Virtualization, which prevents these kinds of attacks. How does that technology work? So as I said, SEV is short for Secure Encrypted Virtualization, and it's actually not a single technology. It's a set of technologies which build on each other. The most basic building block is SEV itself, which provides encryption of guest memory. The next building block, building on top of that, is SEV-ES, or encrypted state. Encrypted state adds the encryption of the guest register state, so that also the guest registers are encrypted and not accessible by the host or hypervisor anymore. So the hypervisor cannot read it and not modify it. And building on that, there is SEV secure nested paging, or SEV SNP, that provides protection against memory remapping and replay attacks. This is currently in the process of being enabled upstream, so not yet available. I will not cover it in this talk. I will focus on SEV and SEV-ES. So how does SEV work? If you enable SEV for your virtual machine, it will basically turn the virtual machine into a black box, or the virtual machine's memory into a black box. So the memory of the virtual machine is no longer accessible by someone with access to the physical machine. All data is encrypted in the virtual machine, and when someone on the physical machine tries to read it, it will only see the encrypted data, not the plain text data. Only when the CPU is running in the virtual machine context, the data can be accessed unencrypted. So only the virtual machine has access to the plain text data. The virtual machine needs to know that it runs in an encrypted environment because it needs to decide which memory is encrypted and which is not encrypted. There are certain parts of memory which are usually not encrypted, and those parts are usually used for the communication between the virtual machine and the hypervisor. But again, it's totally the decision of the virtual machine which memory and how much memory is mapped unencrypted. Usually most of the memory is encrypted. And building on that, there is SEV-ES or encrypted state. This actually causes some problems for the guest operating system and for the hypervisor, because the hypervisor usually needs access to the guest registers to handle certain guest events. With SEV-ES, this is no longer possible because the hypervisor has no access anymore to the guest registers. So it can't handle these events anymore. So these events needs to be handled inside the virtual machine. There's a new exception vector for this, the VC exception, which needs to be implemented by the operating system. And in this exception handler, there's code which would normally run on the hypervisor, but now runs inside the encrypted virtual machine. Every time an event happens which would require the hypervisor to access the registers, an exception is raised inside the guest, and the exception handler handles the request. Usually it also talks to the hypervisor in this process with a peri-virtualized protocol. But in this protocol, the guest only reveals the information which is needed to fulfill the request and not the whole register state. So the whole register state is hidden from the hypervisor, and the hypervisor only gets the information it really needs to fulfill the requests. So how can we use this technology on SUSE Linux Enterprise? I will show you how to set up an SEV-ES virtual machine with libvirt. For that, I extended the virt install command you've seen on the previous slide. So this is the extended command. I highlighted the parts which are new. So first of all, what we need to do is disable the option ROM for the network card, because the option ROMs usually contain code that is not aware of encryption, of encrypted memory, and cannot run in this environment. This will cause problems. It's also not necessary to have it, because option ROMs implement PXE booting, and PXE booting is not considered secure in an SEV or SEV-ES virtual machine, so it needs to be disabled. We disable the auto console, and we disable reboot. That's important, especially for SEV-ES, because for being able to reboot, the hypervisor needs to reset the guest register state. With SEV-ES, the hypervisor can't do this because the hypervisor cannot access or modify the guest register state. So the hypervisor can't emulate a reboot for the guest. Therefore, to reboot an SEV-ES guest, we need to shut it down and restart it. We also need to set a memory hard limit for memory that can be pinned, because the guest memory needs to be pinned for SEV and SEV-ES guests. It cannot be swapped out or moved around. That will not work, so it needs to be pinned in memory, and for that we need to set a limit. We also need to enable EPYC firmware for the guest, because EPYC firmware is the only firmware that is able to run in a confidential SEV-ES environment and is able to boot a standard operating system. And the last parameter is actually the most important one, because it enables SEV for the virtual machine, called launch security. So we tell it to use to enable launch security, run an SEV guest, and use a policy of 7. Policy is a number which represents a bit field, where every bit enables or disables a certain feature. Bit 0 disables debugging. Bit 1 disables that the encryption context of that VM can be shared with other VMs. And bit number 2 finally enables ES encrypted state. When bit 2 is not set, we would run a SEV VM and not an SEV-ES VM. So bit 2 is set, we run an SEV-ES VM. And when we run this command and go through the installation, then we will end up with an SEV-ES virtual machine, which I already prepared here. So let's launch it. So first of all, it will ask us for the disk password. When the memory of the guest is encrypted, it's of course also important to encrypt the disk of the virtual machine, because data can not only be stolen from the memory of the virtual machine, it can also be stolen from its disk image. The hypervisor also has access to that. So it's important that we encrypt the disk image too. Otherwise, our data would not be secure. So we are here. Let's boot our operating system. It's booting up. And shortly, the graphical interface should launch. Here it is. We are now in our SEV-ES virtual machine. So let's check what features are enabled. We can do this by looking into the kernel log, kernel message log, and grep for SEV. And we see that AMD memory encryption features are active, and the active features are SEV and SEV-ES. So we are running in an SEV-ES environment. Here we can put our secrets. Our new secret password. And when we try to attack this VM, now this is a QEMU process which runs the SEV-ES VM. Here SEV-ES is the name. This is the PID. And if we try to attack this VM, then our tool will not be able to find anything, because our memory is encrypted. The host will only see the encrypted content and can't scan the plain text and steal data from it. So let's see. Same here, nothing found. So our VM is really protected, and the memory is safe and secure and can't be stolen from the host side. So this was how to launch an SEV-ES VM with libvirt on SUSE Linux Enterprise. Now Vasily will take over and show you how to use AMD SEV in Kubernetes with KubeVirt.
Thank you, Jörg. Hello, I'm Vasily, software engineer at SUSE. In this demo, I will show how to run a confidential virtual machine on a Kubernetes cluster with KubeVirt using Secure Encrypted Virtualization, or SEV, the memory encryption technology available for AMD EPYC CPUs. I will focus on the specific configuration options required to run an SEV guest and try to show how to avoid the common pitfalls. For the demo, I've set up a test cluster with 2 nodes running SLE15SP4 as the host operating system. And I have already deployed KubeVirt on the cluster. This is the KubeVirt version from SLE15SP4. It is built on top of the official SUSE-based container images, BCI, and it uses the supported SLE virtualization stack. Also, I've prepared upfront a baseline YAML definition for our virtual machine. For now, there is nothing special about it. It defines a SLE15SP4 minimal container disk VM, more precisely the OpenStack version with Cloud on it support. It requests 1 GB of RAM and sets the credential for the default user. Now, in order to enable SEV memory encryption, we need to modify this YAML definition. Here we need to add a new element, which is launch security SEV. That will force the use of SEV in our guest. Additionally, we need to enable EPYC and disable secure boot. Without doing so, the validation of this virtual machine will fail and KubeVirt will reject it. Now this should be ready, and let's save it and try to run the VM. One thing to note here, SEV is a new feature in KubeVirt, and like any new feature, it's not available by default. In order to use it, we need to explicitly enable the workload encryption SEV feature gate in the KubeVirt custom resource configuration. That can be done pretty easily by using, for example, the patch command, which I have in this script. So now let's try to run the VM. And the validation seems okay, and now we have our VM running. KubeVirt automatically detects the nodes in the cluster capable of running SEV guests and advertises this capability. In our setup, we have one such node, which is virt 158, and the VM gets assigned to that one. Let's now attach to the serial console and look what's going on inside the guest. Well, there is nothing that looks unusual actually. We can see a normal boot of our VM, but SEV requires support in the guest kernel, and SLE15SP4 supports SEV, and we can check in the kernel log if this feature is currently active. So we have a confidential KubeVirt VM running in our Kubernetes cluster. Worth to mention that this functionality is now also available upstream. That's all for the demo. I hope you found this video helpful. Thank you for watching. And now I will hand over back to Jörg.
Thanks, Vasily. That was very interesting. Now that we learned how to use AMD SEV and SEV-ES with libvirt and KubeVirt, I want to show you how you can use SUSE Linux Enterprise as a guest operating system for confidential computing in the public cloud. For that, I will focus on the Google Compute Engine, because the Google Compute Engine has a confidential virtual machine offering for quite some time already, based on AMD SEV, and I will show you how to use that now. So when you have an account on the Google Compute Engine, you log into the web page, click on Launch New Instance, enter a name for your virtual machine, and click the Confidential VM Service checkbox. This will make your VM a confidential VM, and it will also make some changes to your virtual machine. So first of all, it will change the series to N2D. N2D is the virtual machine type that supports confidential computing. It will set a new machine type. It will change the zone to one that supports the N2D machine type, and it will choose a confidential OS image. Not all OS images are able to run as a confidential VM, so an appropriate image is chosen automatically. Next, you select the size of your virtual machine. You can select between different amounts of vCPUs, different amounts of memory. Whatever you need in your virtual machine. And then you can choose the operating system between images that are able to run in that confidential virtual machine environment. And you have the choice between SUSE Linux Enterprise Server 15, SP2, SP3, and SP4, among others. So you can use SUSE Linux Enterprise 15, SP2, and newer as the guest operating system in these environments, in this environment. You also turn on Secure Boot and the virtual TPM and also integrity monitoring. These are all security features which make sense with the confidential virtual machine. And after that, you are basically done. You can click Launch to launch your instance. And when it's up and running, you can log into it and check the kernel messages and search for the line AMD memory encryption features active. And there you will see that SEV is enabled in your virtual machine. So it runs in an SEV environment and all memory of your virtual machine is encrypted and not visible to the hypervisor. So that were the tutorials I wanted to show today. What did we learn? We learned that data can be stolen from standard virtual machines pretty easily when the host operating system is not secure, when it is hacked or when you can't trust the owner of the host operating system. And we also learned that you can use AMD SEV and SEV-ES to protect your data in such environments, because this technology will encrypt your data and make it impossible for the host owner to see it. We also learned that you can use SUSE Linux Enterprise 15 SP4 as a host operating system to drive AMD SEV and SEV-ES virtual machines using libvirt and KubeVirt. And we also learned that you can use SUSE Linux Enterprise as a guest operating system for confidential virtual machines in the public cloud, in the private cloud, and on Kubernetes. Finally, I want to mention that all tutorials I showed today, or we showed today, so running a virtual machine with AMD SEV-ES enabled in libvirt, running a virtual SEV machine in Kubernetes with KubeVirt, and launching a confidential VM in Google Compute Engine will appear as separate, more detailed tutorial videos on the SUSE YouTube channel soon. So please keep an eye on that if you want to learn more about this whole technology and how you can use SUSE Linux Enterprise to leverage it. Thanks for listening, and I'm here for your questions now. Thank you.